Hello and welcome to this video. In this video, we will learn about binary trees, specifically binary search trees, and how we work on them and what are the advantages of binary search trees. So what you are seeing is a binary tree in this picture, and the motivation of having such a data structure comes from the previous video where we discussed binary search on a sorted array. So what binary search is that binary search tree is that it gives us a data structure which is in which it is very easy to perform search like binary search. So for example, in this case, let's go through some terminologies first and then we'll see how it works out. So the first node, this 10, is called the root node, and 5 and 15 are its children. In binary search tree, any node can have at most 2 children. They can have 0, 1 or 2 children. Similarly, 5 has 2 children, 2 and 7. So 5 is called father of 2 and 7. For example, 10 is father of 5 and 15. And 5 and 15 are called left and right sons of 10, respectively. Now there is a concept of ancestor. So 10 is ancestor for all the nodes. And all the nodes are descendant of this root node 10. Similarly, you can consider this subtree where 5 is their root. So this is called a left subtree. And the node 15 and all the way up to 11 and 19, this is called the right subtree. So by looking at the diagram, you can easily figure out that we can perform recursion on this tree structure very easily. Now, every element is also called a node. So 1, 2, 3, 4, all are nodes. Now, the nodes which have no children, like 1, 4, 6, 9, 11, 14, 16, and 19, these are called leaf nodes or leaves simply. So let's go through a bit of jargon on how it works out. So the proper one thing I would like to tell you that in binary search trees, every node which is less than root node goes to the left side of it. And every node which is greater than or equal to the root node goes on the right side. So for example, all the items in the left subtree will be smaller than the root node. So if it is 10, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9 are part of left subtree. And whatever is on right hand side is greater than or equal to 10. Similarly, if you consider 5 as root node, everything less than or equal to 5 is on the left subtree. And everything on the right side is on the right subtree. For example, for 2, 1 is less than 2, so it is part of left subtree. 3 and 4 are part of right subtree. So this rule holds true for every node in the binary search tree. So let's go through a bit of jargon. So a binary tree is a finite set of elements that is either empty or partitioned into 3 disjoint subsets. The first subset contains a single element called the root of the tree. 2 other subsets themselves are binary trees called the left or right subtrees of the original tree. Either or both of the subtrees can be empty. Each element of a binary tree is called a node of the binary tree. Now, if A is the root of the binary tree and B is the root of its left or right subtree, there is a typing mistake, then A is said to be the father of B and B is said to be the left or right son of A. A node that has no sons is called a leaf node. A node A is an ancestor of some node B. This is descendant of ancestor node. If A is either father of B or the father of some ancestor of B. 2 nodes are brothers if they are left and right sons of same father. If so, for example, 5 and 15 will be brothers because their father is same, 10. 2 and 7 would be brothers. 1 and 3 would be brothers. 6 and 8 would be brothers. So that's how brothers you can recognize. If every non-leaf node in a binary tree has non-empty left and right subtree, the tree is called strictly binary tree. A strictly binary tree with n leaves always contain 2n minus 1 nodes. The root of the tree has level 0. The level of any other node in the tree is one more than the level of its father. The depth of binary tree is a maximum level of any leaf in the tree. This is equal to the length of longest path from the roots to any leaf. So, for example, 10 will have level 0, 5 will have 1, 2 will have 2, 1 will have 3, and 4 will have 4. Yeah, 4 level. So the depth of binary tree is 4 in this case. A complete binary tree of depth D is the strictly binary tree. There are two R's, all of whose levels are at any level D. The N is missing. Complete binary tree contains one node at level 0, 2 at level 1, 4 at level 2, and so on. On dth level, it will contain 2 to the power D leaves because it is complete. So if you see, if there are no elements after 5 and 15, then these two will be leaves. Okay, so the level is 1. Okay, so the number of leaves would be 2 to the power 1, that is 2. So total number of nodes will be 2 to the power 0 plus 2 to the power 1 up to 2 to the power D is equal to 2 to the power D plus 1 minus 1. Since all the leaves are at level D, total number of leaves is 2 to the power D, and total number of non-leaf nodes is 2 to the power D minus 1. A binary tree of depth D is an almost complete binary tree if any node at level less than D minus 1 has two sons. For any node in the tree with the right descendant at level D, it must have a left son, and every left descendant of it is either leaf at level D or has two sons. This M is missing. So this is the jargon of binary search tree. Now let's go and look at the implementation of binary tree. So we have this main function where I have defined the node. This node type is defined in this header file. This is the node. So node is defined like it can contain data. So it can be integer, float, character. It can be struct also. It can be anything. But this is the data portion. For simplicity, we are considering integer. And it has two children of the same type, left and right, so that it can point to other nodes. Now we have 5 functions here: new node, insert, get max, delete, and find. We'll see how to use these. Let me close this one. So in the main function, we have root as null, option as -1, and data is 0. Now this is a simple event loop. Okay, it's not really an event loop, but basically you insert 1, 2, 3 for operations and 0 for quitting. And based on the option, if it is 1, then we call insert routine. If it is 2, then we call delete routine with data. We pass the root and data. And in case it is 3, we search for the data in the binary tree. And then we accordingly print whether it is in the tree or not. Now let's first look at the insertion routine. So insertion, if root is null, we create a new node and make that root. Okay. The creation of new node is very simple. We pass it data. We allocate the node, memory for node. We set data member as data and left and right as null for the new node, and we return the pointer of this. So if root is null, then we create the node and make it root. Otherwise, if data is greater than root data, then it will go to the right subtree. So we call insert with root right element. So it will go to the right subtree, and then that further it can go in any direction. And if it is less than root data, then we choose the left subtree and pass the root left as the assignment. So this is how it works. Okay, and finally we return the root. Now delete is tricky. Let's first deal with find. So when you find, we have the root and data. If root is null, we return 0. If data is greater than root data, then we operate on right subtree. If it is less than root, then we operate on the left subtree. And if it is equal to data, that is root's data, then we return 1. Otherwise, we finally return 0. So this is the basic search scheme. That's why I said recursion is very easy very much applicable in binary search trees. Now we have delete. So how we do the deletion? So some cases are very simple. If root is null, we return root. Else if root is greater than data, then we delete. We call delete on the right subtree. If it is less than root data, then we call delete on the left subtree. Now, if data is equal to root data, then there can be several cases. That is, left and right children are null, then we simply free the element and return null. But if left subtree is null, okay, then what we do is we copy the root pointer into temp and we make the right of the node, because right subtree exists. So we take the right subtree's root and we make that root, and then we free temp and we return root. But if right is null, then simply we perform the corresponding operation like the right one, that is, we pick the left subtree and make that root and return root. I will show in the diagram how it will all work out. Now the most complex case is when it has both the leaves, that is, both the subtrees are there. So in this case, we find the greatest key in the left subtree and switch that with root. Alternatively, you can find minimum in the right subtree and you can use that. So I call get max on left subtree. Once we have this node temporary, we assign the temporary data to root data, and on root left we call delete. Okay, so that's how it works. Let me try to explain this a bit. Okay, the last case, because first three is very easy. Consider there is a binary tree here 10, and we have its children. Okay, suppose this is the case. Consider this. Okay, so in this case, suppose we want to delete 10. Okay, then this case will apply here. So what we will do is we get max of root left. So max is 5. It can have more children here. Say for example like this, 8. Okay, so get the max of root left, that is 8. And then we copy root on the root data, we copy temporary data. We copy this 8 to here. So it will become 8. So that is the greatest value of left subtree. And then this can be a tree in itself. For example, it can have left children. Okay, like this. Say 6, 7, or 6. Okay, but it can't have right children, because if right children are there, then that would become the maximum. So in this case, we do that, and then we call delete on root left. So in this case, root left is 5. Okay, and we have the temp data, right? That is yeah, get max root left. So this data will be there. So now we want to delete this data, we supply with 5. Okay, that is our root left, and 8 we are supplying with to delete 8. So the operation will recursively delete the elements appropriately. So I hope that this example would have become made it clear. So now with this done, let's take a look at the run of GCC. So I compile it and then I run it. So first we insert a node 10, then we insert a node 5, 6, then we insert another node 9, then we insert another node 15 or 15, and now let's try to find the node 15, and we try to find again, let's say this time we want to find 6, So the values are in tree. Now we want to delete something. We want to delete 6. So 6 is deleted. Now let's see if we can find 6 again. So 6 is not found. That means it is deleted. Here 6 was found in the tree. So now you see that this program is working, and you can test for yourself. The most important part about binary search trees is that the search operation is log n, and a log of n with base 2, and insertion can be, worst case could be on, because in a skewed binary tree you can have a tree like this, say for example 10, and then we can have all the terms on left hand side, 12 and 15. So this is the right skewed binary tree. So in such a case, insertion is on, worst case, and search will also be worst case. But if a tree is balanced, then the search would be log n. So the main motivation of using binary search tree is to have log n search time. Now, if the binary tree is not balanced, that is, it is not close to complete binary tree, then search and insert and find all operations worsen to O of n. That is big O of n. Therefore, we have advanced data structures like AVL tree or red black tree, which are self-balancing binary trees, and they do not deteriorate the insertion or the search complexity. With that, I will leave here, and in the next video we will see more operations on binary search tree. I will introduce more functions, and we will see how we go from here. So if you have found this video useful and informative, please subscribe to the channel and like the video. If you have a comment or suggestion, or you want to say something, then please make use of the comment box, and do not forget to click the bell icon so that you can receive notifications about new videos coming in the channel. Thanks a lot for watching. Happy programming.